What if I told you that volcanoes don't always erupt fire and lava? Some of the most explosive mountains in our solar system actually erupt ice. Picture a volcano. You're probably imagining a towering mountain, billowing smoke and rivers of red-hot lava. But what if I told you that some of the most active volcanoes in our solar system are the exact opposite? They're cold, they're icy. And instead of molten rock, they spew frozen water, ammonia, and methane. These aren't science fiction. They're cryovolcanoes, and they're reshaping worlds right now. The discovery of cryovolcanoes turned planetary science upside down. For centuries, we thought volcanic activity required extreme heat and molten rock. But when spacecraft started sending back images of icy worlds with mountain-like structures and fresh, smooth plains, scientists realized something strange was happening. These weren't impact craters or ordinary mountains. They were volcanoes that operated in deep freeze. Let's start with what makes a cryovolcano so different. Regular volcanoes, like those on Earth, happen when molten rock from deep underground finds a path to the surface. The heat comes from our planet's radioactive core and leftover energy from its formation. But on icy moons and distant dwarf planets, the heat source is completely different. These worlds are too small to retain the kind of heat Earth has. Instead, their internal warmth comes from tidal forces, the gravitational tug-of-war between them and the massive planets they orbit. This constant stretching and squeezing generates enough heat to melt subsurface ice into slushy, salty water. When pressure builds up, that mixture erupts through cracks in the icy crust, freezing instantly in the vacuum of space. The result isn't a river of lava, but a geyser of ice crystals and liquid water that freezes into smooth, glass-like plains. One of the most famous cryovolcanoes sits on Saturn's moon Enceladus. This small, bright moon looked unremarkable until the Cassini spacecraft discovered massive plumes of water vapor and ice shooting from its south pole. These weren't random geysers. They were erupting from 4 parallel fractures nicknamed tiger stripes. The material being ejected wasn't just water. It contained organic compounds and salts, suggesting it was coming from a global ocean buried beneath the ice. Every second, Enceladus launches hundreds of kilograms of material into space, some of which even forms one of Saturn's rings. Then there's Triton, Neptune's largest moon. When Voyager 2 flew by in 1989, it captured images of dark plumes rising several kilometers above the surface. These weren't smoke. They were nitrogen gas and dust particles being ejected from beneath the ice. Triton's surface is one of the coldest places in the solar system, yet somehow it has active eruptions. The driving force here is sunlight. When the sun warms dark material on the surface, it vaporizes subsurface nitrogen, building pressure until it bursts through the ice crust in spectacular plumes. Perhaps the most intriguing cryovolcano candidate is Pluto. When New Horizons flew past in 2015, it revealed 2 massive mountains that look nothing like impact craters or ordinary hills. These features, named Wright Mons and Pickard Mons, have central depressions and wrinkled slopes that closely resemble shield volcanoes on Earth, except they're made of water ice. Scientists believe these might be giant cryovolcanoes that once erupted a mixture of water, ammonia, and methane slush. The presence of ammonia is crucial because it acts like antifreeze, keeping the mixture slushy at temperatures where pure water would freeze solid. What's fascinating is how these cryovolcanoes create environments that could potentially support life. On Enceladus, the erupting plumes contain almost all the ingredients needed for life as we know it: liquid water, organic molecules, and an energy source. The same tidal heating that powers the eruptions also keeps the subsurface ocean liquid. Similar conditions likely exist within Europa, Jupiter's moon, where cryovolcanic activity may be replenishing the surface with fresh ice from the ocean below. The study of cryovolcanoes is teaching us that geological activity isn't limited to rocky planets. Icy worlds can be just as dynamic, with their own version of plate tectonics, mountain building, and volcanic activity. Instead of silicate rock cycles, they have water cycles where material from deep oceans reaches the surface through cryovolcanic eruptions, then gets recycled back down through subduction or burial. This changes how we think about habitable zones in space. We used to believe life could only exist in the Goldilocks zone, where liquid water can exist on the surface. But cryovolcanoes show us that life could thrive in completely frozen worlds, as long as there's enough internal heat to maintain subsurface oceans and volcanic activity to circulate nutrients. The future of cryovolcano research is just beginning. New missions are being planned to Europa and Enceladus specifically to study these icy eruptions up close. Some proposals include flying through the plumes to analyze their composition, or even landing near cryovolcanic vents to search for signs of biological activity. What we learn could fundamentally change our understanding of where life can exist in the universe. Which icy moon do you think is most likely to host life? Enceladus, Europa, or Triton? Let me know in the comments, and subscribe to Nature Unlocked for more mysteries of our incredible universe.